We've talked about vector addition, but not yet about vector multiplication. Multiplying vectors is a little bit more complicated because of the fact that vectors have both a magnitude and a direction. So actually, both forms of multiplication of vector, and there are two forms, so there are two kinds of products that we'll refer to, deal in various ways with assessing the direction, the relative direction of two vectors. So the two kinds of multiplication go by the name of the scalar product or the vector product. There's also sort of the more colloquial name, the dot product, given to the scalar product, or the cross product. Given to the vector product. We'll see why that's so in a moment. Let's deal with the scalar product first. If I have two vectors, A and B, and they have some different magnitudes and a relative angle between them, we call the dot product A dot B. This product produces a number. So if this is 5 in the north direction, this is 3 in the east direction. It just produces a number. And the number that it produces is the magnitude of A times the magnitude of B times the cosine of the angle between them. So it doesn't produce a new vector or anything, which is a little bit different than traditional multiplication of integers. If I multiply two integers together, I get another integer. Or if I multiply two real numbers together, I get another real number. This kind of multiplication, I multiply, or I take the dot product of two vectors, and I get back a scalar quantity. So if I happen to know the magnitude of A, and I happen to know the magnitude of B, and the relative angle between them, I can compute this dot product rather easily. There's another technique, which is if you know the components of A and B, I can simply multiply the components out. So AX times BX plus AY BY plus AC BZ. Again, the result is a scalar. It's not always the case that the scalar has to be a positive number. So for example, while in this case, if this is A and this is B, this little cartoon produces a dot product that's greater than 0. In fact, it produces a dot product that's equal to the product of the two magnitudes because I've drawn them parallel. So the angle between the two vectors is 0, and the cosine of that angle would be 1. And so A dot B would just equal A times B. But notice if this was A and this was B, in this case, A dot B would equal minus times the product of those magnitudes. This would be less than 0. Because now I've drawn them antiparallel. In other words, the relative angle here, phi, is 180 degrees. They point back to back away from one another. The cosine of 180 degrees is minus 1. Here's an example where A dot B is exactly 0 because I've drawn the 90-degree angle between the two vectors. The second product is called the cross product, and if A and B are two vectors with a relative angle phi between them, the cross product for A and B is a new vector. And this magnitude of this new vector will be A times B times the sine of the angle between them. I haven't described how to determine the magnitude of this new vector, but it points up and out of the plane between A and B. So while the dot product is a measure of how well aligned two vectors are, because there's a cosine here, and it becomes large whenever the two vectors are in the same direction, this cross product becomes large when the two vectors are perpendicular. So this produces a result which is a vector. And just to think through some of these examples again. In this case I've just drawn, the vector product is actually 0. Because the angle between these two vectors A and B is 0 degrees, and therefore the sine of the angle between them is 0. So the cross product, again, is a measure of how perpendicular the two vectors are, and these are not very perpendicular vectors. On the other hand, if I'd drawn A over here, B over here, and this was a right angle, this would be C. So if this was in the x direction, that was in the y direction, the vector C would be in the z direction. And it would be the largest possible magnitude it could be. It would just be A times B. There'd be no multiplication of the sine of an angle because, well, the angle is 90 degrees between A and B. And as a result, the sine of 90 is 1. On the other hand, if this was A, and this was B, this was the x direction, and that was the y direction, C would point straight down. And the vector C in this case would be -1 times the vector C in this case. There to point straight down the minus C direction. It would still have the same magnitude, just pointing in the opposite direction. Now, how did I know what's the relative orientation about C and A and B? So far I've only talked about the magnitude, how to compute the magnitude of this cross product. I haven't said anything about how to compute the direction. And remember, since the vector product produces a vector result, I have to specify both a magnitude and a direction. So the scalar product just produces a scalar result. I just need to tell you how to compute the magnitude of it. The vector product produces a vector, and I have to tell you both how to produce the magnitude of that vector and the direction. So let's turn our attention to the direction. There's what's known as the right-hand rule in physics, and the right-hand rule teaches us how to compute the direction or estimate the direction for a cross product between two vectors. If I have two vectors A and B, and I form a sort of shape with my right hand, I have to use my right hand to do this. I point straight ahead like a little pistol, I suppose, and move my middle finger off to the side in the direction of B. My thumb points in the direction of the cross product. So this tells me that in a situation where A points that way, B points straight down, then if I were to use my right hand, notice that my thumb is coming straight up out of the page. So C would look like if you were standing over a rocket and it was launching right at you, you would see only the tip of the rocket. We sometimes note that with a little circle and a dot in the middle. On the other hand, if this was B, and that was A, where would C point? Well, by the right-hand rule, C would point straight into the paper. So this is when we draw a circle with a little X through it, this is the opposite of seeing the tip of the vector for the rocket. This is like seeing the tail, and it's heading away from us. So this becomes a bit of a three-dimensional challenge. We have to get used to the idea of how to gauge what this direction is going to be using our right hand. Some people also use the right hand rule in a slightly different way. If you point all your fingers out in the direction of B and then curl them toward B, like so, it forces your thumb to point in the direction of the cross product. So you start at A, curl them toward B, and you form what the direction of the cross product is. We haven't said anything about the magnitude. The right-hand rule simply tells you something about the direction, and the magnitude comes from our previous prescription.